Our next speaker is the of AI and ML and cloud partner engineering at Google, and is here to talk about challenges and ethics of language models and large language model adoption in the enterprise. So please join me in welcoming to the stage Ali Arsanjani. Welcome, Ali.
Hi, thank you. Hope you can all hear me well. Ali Arsanjani, and I lead partner engineering for Google Cloud, specializing in the area of AI/ML. And very happy to be here today with everyone. Today, we're going to be talking essentially about how a responsible generative AI model adoption can happen at the enterprise level, and what are some of the promises and compromises we face. So we're going to look at a very quick rendition of the evolution of LLMs and foundation models, take a look at LLMs at Google, and then look at enterprise applications. What are the promises? What are the challenges and compromises? Then we're going to talk about adapting foundation models for the enterprise and how that affects the ML lifecycle and what we need to potentially add to the lifecycle. So the foundation of large language models started quite some time ago. And essentially what led to foundation models is large language models being a subset of foundation models. And the whole generative AI, if you will, movement was basically taking a vast amount of training data, specifically textual data. And of course, there are multimodalities in the other generative AI capabilities and models, and training them as a basis for other models. So there's obviously an evolution, and then it came to its own with the creation of the transformer architecture, Google's BERT, OpenAI's GPT-2, and then 3, Lambda for conversation, Mina and Sparrow from Google DeepMind. So really quickly, LLMs can do many things. One is obviously the most popular these days, which is a conversational agent, human-like dialogue, and in conversational context. We can have code generation in the same mechanism, write code with a natural language description and start modifying that code, translating code from one language to another. It can do reasoning, extractive question answering, common sense reasoning, joke interpretation, multi-step arithmetic, and essentially using standard prompting and chain of thought prompting. And then there's some degree of conceptual understanding that can be awarded to large language models. They can distinguish cause and effect, and then combinations of various appropriate contexts. So as we look at the session, we see that these state-of-the-art NLP models very specifically are getting larger and larger over time, with currently the largest one, the Pathways language models, 540 billion parameters. And these are obviously not just focused on one task, they are focused on many, many downstream tasks and activities. And the capabilities they have stem from the fact that they are leveraging some pathway within the neural network, not the entire neural network necessarily. About significant amount of researchers at Stanford and other places got together and built this paper. We're just going to refer to as the foundation model paper. This was effectively an academic rebranding of what initially was these large language models, and then different modalities came into being, and the fact that they have to be fine-tuned with in-context learning and adapted to a wide stream of downstream tasks and applications caused this movement to be very appropriate at its time. And there are basically two ways of looking at a representational and generational viewpoints in foundational models that approach the problem of how do we build foundation models, such as language models. The representation viewpoint looks at it from the input text and input data perspective, where you have a pre-training of a large data set of unannotated text in representation, whereas in the generation viewpoint, you have a large data set of annotated text. In the representation view, you can fine-tune on specific tasks to improve performance. And you can also do that in the generation model. Obviously, the generation model is good at generating text that's similar to the input, but it may not be able to learn general representations of the data and to capture the underlying patterns and infrastructure in the data. Whereas the representation view is very good at learning representations of the data, the underlying patterns and capabilities, underlying structure, but may not be able to generate text. And there are mechanisms in terms of combining these approaches. So this foundation model paper explored these opportunities and risks of foundation models, where you take a small, lightweight LLM trained on a diverse set of tasks in an unsupervised fashion. And we discuss the effectiveness here of the foundation model as a starting point for fine-tuning on downstream tasks. So this paper is about 200 pages, so there's a lot to read. If you're interested in looking, it's more encyclopedic. It's not necessarily one cohesive read. You can look at it from different angles. One of the angles in which we're going to look at it today is this adaptation for enterprise implementation of LLMs and foundation models. And of course, foundation models have various, if you will, degrees of freedom or hyperparameters almost. These are the parameters of the model. They are exponentially big, different tasks, different modalities, and basically has a pretext task to reconstruct the input or parts of the input. And there is an amount of external guiding that occurs. From a software engineering perspective, machine learning models, if you look at it in terms of the number of parameters and in terms of size, started out from the transformer models as we discussed. And gradually, as folks adopted the transformer model and various architectures of the encoder-decoder architecture, they started growing these language models and make them applicable to very specific areas, such as interpreting strings of amino acids like an AlphaFold that make up proteins, and help us advance our understanding, basic building blocks of biology, and just to name one very specific example. So the application started to go from the pure software engineering, machine learning domain to industry and the sciences, essentially. So looking at what the capabilities of all these different large language models, and there are a significant number of them, basically this kind of ends in August 2022 here. Billions of parameters, very large corpus, and very efficient in certain sets of things. Some of them are more geared and tuned towards actual question answering or a chatbot kind of interaction. Others, language completion and further downstream tasks. One interesting observation is that there's the Gopher one from DeepMind and Chinchilla, which was a much, much smaller version of Gopher, but it demonstrated that even a much smaller distilled model can work as well or almost as well if the right parameters are chosen and the right paths are chosen through that model. So within Google, we can see the progression of large language models starting from the transformers, BERT, and then the T5 model, Lambda, which is the language model for dialogue-based applications. There are various offshoots of that, Mina and Minerva, and etc. And then the pathways language models, and lately, the confident adaptive language models, which is a version of PaLM. I've provided you with some links here. You can check them out later on what these Google dialogue-based, very focused on dialogue-based LLMs can do, which ones are, kind of state of the art. One of the latest ones is Sparrow, which is in the paper Improving Alignment of Dialogue Agents via Targeted Human Judgments. And Sparrow is basically an open domain dialogue agent that's trained to be more helpful, more correct, and more harmless. And it does so through three things. It employs reinforcement learning from human feedback. It actually provides evidence of the claims it makes. And there are a set of rules that it abides by, essentially. And some of these rules, if you look in the paper, are outlined here. And so humans were asked, how did this response violate which of these rules? And the humans, in a reinforcement learning-based approach, provided feedback on this. So this set of rules makes this kind of dialogue agent less harmful and, essentially looking at all these things like no threats, no harassment, no microaggressions, no general harm, no insults, no legal advice, no identity attacks, et cetera, et cetera, et cetera. So these are elements that gradually make it safer and safer for us to think about enterprise applications, what the promises are, what the challenges are, and what the compromises are. There are definitely compelling economic reasons for us to enter into this realm. Now, the suitability of these models for widespread deployment is yet somewhat uncertain, even though models are out there today. And it's important to be very cautious and establish some professional norms for responsible research and deployment. And so with that, there are some elements of LLMs in the industry that can be applied, such as for customer support. The natural chatbot, conversational agent, or contact center, comes to mind in terms of technology, generating code snippets, code translation, automated documentation in financial services, summary of financial documents, entity extraction, and in healthcare, various domain-specific entity extraction, case summarization, and of course, there are specialized models like AlphaFold, which actually get into genetics and protein binding, etc. In retail, generating product descriptions and recommendations and return and these types of things. In media and gaming, designing game storylines, scripts, auto-generated blogs, articles, and tweets, and grammar corrections and text formatting. So there are potential risks associated with each one of these in each of the domains, even though there's a use case. For example, I'll just take a look at one of them. Large language models can be used to analyze medical records and extract relevant information, like a diagnosis or treatment plan. But the accuracy is important so that it can cite information of why it made that diagnosis or why the treatment plan is recommended. So these types of risks are mitigated by language models that actually provide those types of further adaptation than just the generation of a cohesive answer. I'm actually not going to go through every single application in healthcare, finance, retail, manufacturing, and education. These are obviously areas that we can look at them. They're areas in collaborative application, like in your word processor, in your spreadsheets, etc., in your contact centers, even inside your Jupyter notebooks, all areas where positives and negatives reside. But in order to actually adapt the foundation model or generative AI process into the enterprise, we need to look at what the changes, potential additions that we may need to make are to the. Here, we're just going to look for a quick second at a lot of the open source kinds of things that have been happening, as specifically focusing on what Google has open sourced and produced and provided a scalable infrastructure to run these things on. And of course, Google Cloud provides this scalable infrastructure for us to run our workloads, whether we're doing large language models and foundation model building or fine tuning and so on, can cover the gamut. And of course, there are a number of traditional machine learning activities across the life cycle that we do: data preparation, train and tune, deploy and monitor. But these are not going to be adequate for supporting generative AI. So this very typical model needs to change. And the way it changes is not just through adding a fine tuning towards the end here. That's not enough, but rather to make sure that we're aware that just fine tuning and performing transfer learning in the era of large language models may not necessarily be adequate, whichever of these types of models we're using. And so the adaptation has to be coming into account along with the fine tuning. And in the adaptation, you're creating a new model based on an existing foundation model. Yes, you're fine tuning in some shape or form. Maybe you're prompt tuning, etc. But it involves additional modules, custom rules, evidence, and classifiers of the model, as well as combining it with other complementary signals. And we're going to explore what these signals are. In the context of enterprise deployment, adaptation is very, very important for identifying and mitigating the potential harms that can be caused by problematic models. And so if you kind of distill it down, some of these laws, quote unquote, or recommendations for foundational model enterprise adoption, adaptation very specifically needs to take into account more than fine tuning. It needs to take into account adaptation drift. So you've adapted the model and now it's supposedly safe, But over time, does it remain safe? Similar to when you train a model, it has a certain degree of, let's say, an F1 score or accuracy or what. Over time, you monitor its drift. And in the same way, you need to monitor adaptation drift and add that to the ML lifecycle. And the responsible AI measures pertaining to safety and misuse and robustness are elements that need to be additionally taken into consideration. Number two is the model transparency and reproducibility. Yes, everybody publishes model sheets, hopefully more and more, but the training context, the background, the training scenarios used, the usage scenarios, the toxicity, polarization, misinformation, all these factors pertaining to the model and whether they have been tested on the model needs to also be incorporated in the model sheets. And of course, this goes into the model risk management in analyzing the metadata around the model, whether it's fit for purpose with automated or human in the loop capabilities. So let's take a look at this, what the breakdown is. So we have data pipelines and data preparation. We have adaptation. We have experimentation and in the training and hyperparameter optimization phases, deploying, monitoring, and managing, and prompt engineering. Okay, let's spread out these cards here and get into a little bit more detail. So each of them may require some repositories, from a data lakehouse, analytics hub kind of thing for sharing data, to a feature store, to a model hub, to the responsible AI, known sets of things that you need to guard against, to a model registry, and a database of prompt examples may need to be required for each of these phases. So let's check out what some of these phases look like in more detail. So in the data pipeline phase, I'm just going to call out things that I think are more important than the obvious. So the basic ones are collect and validate and prepare data. But then there are preparations for domain-specific data. Think, biology, think genomes, think financial services applications, very specific data and very specific downstream tasks that need to be evaluated again at that data stage for safety, privacy, bias, etc. in the data, because that's the data that's going to be training the model. And if the data has those biases in them, the trained model will also have those biases embedded in them. So in the data preparation, you obviously clean, normalize, and standardize your data, and you curate and label the data. This is one critical area that's a big bottleneck. Snorkel AI is an excellent advocate of unblocking this in the enterprise. So some of the negative aspects of using foundation models in this respect are that single points of failure may occur because the foundation model becomes that could be a single point of failure that's a prime target for attacks against applications derived from this model. It can be alternatively, on the flip side of the coin, imbued with very strong security privacy properties that could form the backbone, and everything else derives from it. So these are the two sides of the coin. Data poisoning in terms of permissive data collection, where there's lack of direct training supervision, could inject hateful speech, for example, targeted at a specific individual, a company, or a minority group, and may be exacerbated by growing size and accuracy of today's models. There could be function creep and dual usage, where you could be challenged to constrain or foresee possible nefarious uses of foundation models or misuses of the model at design time. For example, CLIP is a model that was originally trained to the generic task of predicting image-text pairs. But in doing so, it actually learned to capture rich facial features. But the model card doesn't show that. It doesn't really show that it could be used for surveillance. That was deemed out of scope, for example. And this example illustrates that it may be challenging to constrain the possible nefarious misuses of a foundation model. And of course, when you have several models of modalities of models, and the adversarial attacks may attack one type of modality and not the other one. Let's say in an autonomous driving system, it could primarily see a billboard with the word green on it and mistakenly interpret it as a green light if it's a multimodal model. Now, on the positive side, it could act as its security choke point in a positive way. Defense against poisoning, against model stealing, or resource depletion attacks. There could be private learning that is cheaper because typically these foundation models are trained on public data. They could be adapted to perform tasks with significantly less amount of confidential data. And then there's robustness to adversarial attacks at scale, understanding how best to leverage this overparameterization and unlabeled data to achieve adversarial robustness. And given their unprecedented scale, they're uniquely positioned to benefit. But FMs are seen to have little gains in robustness to worst case adversarial perturbations. So the key takeaway here is that robustness is a big deal. Robustness to distribution shifts in real world machine learning systems. You need to make sure that there is a system where the robustness is checked and maintained and monitored. There are still ways in which we can affect robustness, like, for example, freezing a foundation model and training only the head. This can lead to better out of distribution performance than just fine tuning the entire model and less costly. But the full fine tuning can distort the pre-trained features in even a simple setting. But it's still poorly understood why freezing the parameters seems to improve out of distribution performance. So current adaptation methods may suffice for good in distribution generalization, but they may not suffice for out of distribution or domain adaptation situations. So the key takeaways and changes for adopting LLMs in terms of the changes to the life cycle are the safety, which include privacy, bias, toxicity, polarization, IP mitigation or IP infringement types of things via traditional rules or adversarial detection models, and misuse and robustness components. And of course, making sure that the actual model sheets reflect what these were intended for and potential side effects of what they are, and to monitor for adaptation drift and not just for things like skew. So adaptation requires not just fine tuning, where you can actually distill models, but improve upon them by using these safety, misuse, and robustness guards. So in terms of AI safety, there is something called the control problem, where an advanced AI system enables us to reap the computational benefits while at the same time leaving us with sufficient control so that when we deploy the system, it doesn't lead to a catastrophic event. And so that mitigation of the control problem is something that AI safety is concerned about. There is this thing called Goodhart's law, which discusses the risks of optimizing misaligned yet easy to specify goals. The short term, the low-hanging fruit. For example, engagement in social media. The negative effects of some recommender systems like polarization and media addiction, which may optimize simple engagement metrics, but are difficult to understand the harder to measure combination of societal, political, and consumer impacts that they may have. So someone could easily misuse and take from a foundation model generator, combine elements together, and target very specific populations with fake profiles, fake news, and abuse. So detecting these types of misuses becomes a critical part of the adaptation phase. So again, content quality, because it could empower disinformation actors, maybe even states, to create content to deceive foreign populations and generate high quality potential deep fakes. There is an imperative to have models that can detect the quality content that could be generated by these foundational models, but are being misused. And the cost of the content creation is lowered. So again, this becomes easier. The personalization and hyper targeting becomes enhanced. So social media posts could be crafted to push certain narratives and target certain populations. So with this, we have to rethink how human interventions come about. For example, malicious practices are uncovered on social media, sometimes removed by humans, by searching the internet to uncover content origination. This is where the evidence becomes important. So disinformation websites frequently use plagiarized content to mask deceptive content, and foundation models can be used in this regard, but need to have that mitigation so that the actual references and evidence is supplied along with it. And the detection of these foundation models for misuse is also enhanced. Okay, very good. So this is kind of the broad discussion around, okay, we've curated the model, experimented with it, done the adaptation. Now we can deploy and monitor it. And then comes prompt engineering. So prompt engineering cannot be think of as a very simple matter. Now it's very experimental. People just basically try different prompts. You will pretty soon need some kind of a database of prompt, the ones that have been more successful, to select, to generate or test prompts and iterate over them based on the domain and downstream activity that you have. So these represent kind of the fifth stage. So 1 is the pipeline, 2 is the experimentation with the training, 3 is the adaptation, 4 is the deploy, monitor, manage, 5 is the prompt engineering, and then you get into ML ops. So in terms of an enterprise, the safety, the robustness, and the anti-misuse factors should take into account these types of elements here. So you can use various mechanisms to build LLMs. The Google Cloud Platform has these capabilities that can be used to put reference architectures to pre-train and fine-tune LLMs on the Google Cloud Platform. I've been asked before that, how do we actually build with the Google Cloud program? So there's a program that can be utilized if you're interested in building with the Google Cloud program. So with that, I'd like to thank you very much for listening to this talk. And if you have any further questions, you can use this QR code to submit questions.